If you have ever looked up at a perfectly clear night sky, you know the feeling. It's that sudden, visceral sense of scale that hits you, right? Where your entire existence just shrinks down to, well, an insignificant speck.
Yeah, absolutely. And that feeling, that's actually the ultimate psychological hurdle for anyone trying to study the cosmos.
Exactly. We are creatures built for human scales. We measure our lives in meters, minutes, and years. Pretty manageable.
But the universe,
Hmm.
it operates on what the great astronomer Joseph Shklovsky, whose work we're really digging into today, simply called the monstrous scale.
Monstrous. That's quite a word.
And, it isn't hyperbole. He really meant it.
Mm.
If you are a professional astronomer, you absolutely cannot allow yourself to dwell on the true dimensions of space and time. It's just too much.
Much how?
Well, if you internalize the full scope of that immensity, if you pause to really contemplate the sheer number of zeros in, say, a distance measurement to another galaxy,
Mm.
the work stops. Automatically. It's profoundly paralyzing.
Okay, let's unpack this. Our mission today, in this deep dive, is basically to take these dizzying dimensions and give you the mental models, the necessary conceptual shortcuts that astronomers themselves use just to function day to day.
Right. We want to build a framework, sort of a mental toolkit for understanding cosmic distance. We'll start right here from Earth's orbit and expand outwards all the way to the limits of the observed metagalaxy.
And then the really cool part, I think, is mapping that immense sweep of time onto a single calendar year. See where we fit in.
Yeah, that's always eye-opening. But the most fascinating insight right at the start is Shklovsky's own admission about this coping mechanism. He says professional astronomers must consciously forget the true scale of distance and time.
Forget it, or just ignore it.
Well, maybe compartmentalize is a better word.
Yeah.
They have to prioritize the mathematical relationships, the relative sizes, the physics, over the actual dizzying numbers themselves. Otherwise, paralysis.
He gave a brilliant personal anecdote about this, didn't he?
He did. It's about when he was studying, say, the solar corona, that vast hot gas around our sun, and comparing it to the structure of the galactic corona, which is this vastly, vastly larger gas cloud around the entire Milky Way.
How much larger are we talking?
Hundreds of billions of times bigger.
Yeah.
Just completely different scales.
Okay. So how did he handle that in his notes?
Well, he said he would sketch both of them in his notebook.
Mm.
And the sketches. They were both just simple spheroidal bodies, roughly 10 centimeters across on the page, visually identical.
Wow. So he just drew them the same size, even knowing one was billions of times larger.
Exactly. He knew the scale difference intellectually, of course. But in his day-to-day work, grappling with the equations, that enormous difference had to be reduced to nothing more than like a formal mathematical coefficient, a number in an equation.
So don't think about the reality, just the math.
Pretty much. Because if that immense difference, the distance, the sheer emptiness of the space, the vacuum, if that became a philosophical sticking point, if you pause to muse on, the insignificance of our small planet lost in that gigantic system,
Like work stops, like you said.
the ability to calculate and observe would simply shut down. So this intentional mental reduction, making the impossible tangible through small sketches or compressed equations, that's the first and maybe the most crucial tool in the astronomer's kit.
It sounds like the first step to conquering the universe is simply refusing to let its scale overwhelm you. Okay, so let's build our own toolkit of scale models, because we definitely need to compress these distances right away.
Good idea. What models are we focusing on? We'll use three main mental models today, drawing from Shklovsky. There's the classic billiard ball analogy for the solar system, then the geometric precision of the parsec for stars, and finally, a really wild one, the hypercompressed Bohr atom scale for the whole shebang. Okay, sounds like a plan. Starting small then.
Yep. Let's begin right here, leaving human scales behind.
Yeah. So to start grasping cosmic scale, we really have to first appreciate how recently we even conquered global scale. Think about how rapidly our ability to cross distances has accelerated just in recent history.
Oh, absolutely. For most of human history, just getting around the Earth was an affair of years, wasn't it?
Yeah, Magellan's loyal crew, this was over 465 years before Shklovsky was writing. It took them more than 3 years just to circumnavigate the Earth. Can you imagine? A monumental feat of endurance back then.
3 years. Wow. And then you fast forward a couple of centuries, you get to the late 19th century, and Jules Verne writes about his fictional hero, Phileas Fogg.
Around the world in 80 days. Using the latest tech of the time, steam trains, steamships.
A huge leap, down from 3 years to just 80 days. Still a long trip, but vastly faster.
But then the really big jump. Just 26 years before Shklovsky published this specific text we're looking at, you have Yuri Gagarin, the first human in space.
And how long did it take him to circle the Earth?
89 minutes. Minutes. From years to days to minutes. In what is, cosmically speaking, the blink of an eye.
It's this massive technological acceleration that really forced humanity, maybe for the first time, to look beyond the terrestrial and confront just how isolated our small world truly is.
Yeah, once you can circle it in an hour and a half, you start wondering what's further out.
Right.
So let's set our first standard unit of measurement, one that's essential for understanding our immediate cosmic neighborhood,
Yeah.
the astronomical unit, usually called the AU. Okay, what's that define?
It's simply the average distance from the Earth to the Sun. Nice baseline. And it clocks in at about 149.6 million kilometers. Let's just call it 150 million kilometers for simplicity.
Okay, 1 AU is 150 million kilometers.
Yeah.
How does that help us size up the solar system?
Well, using the AU, the sheer size starts to become a bit clearer, though it's still pretty abstract. If we think about the space out to the major planets and maybe out to the Kuiper Belt.
Where Pluto and similar objects hang out.
Exactly. The sort of effective size of the solar system is generally placed somewhere between 50 and 100 AU across.
50 to 100 times the Earth-Sun distance. So that's, carry the one, roughly 7.5 to 15 billion kilometers across.
Yeah, around 10 billion kilometers is a good working number for the main part. And Pluto, which was considered the farthest planet when Shklovsky wrote this, orbits at about 40 AU, so 40 times farther from the sun than Earth is.
10 billion kilometers. It's still just a huge number, hard to visualize.
Totally.
Which is why we need our first mental model, the billiard ball analogy. This one is absolutely indispensable for getting a feel for the solar system layout.
Okay, how does it work?
You imagine the sun isn't our star, but just a standard billiard ball, about 7 centimeters in diameter. Pretty small.
Got it. Sun equals 7-centimeter billiard ball. Where's Earth?
Okay, on this scale, Earth is not only incredibly tiny, its radius would be just slightly over half a millimeter, like a grain of sand.
Wow, tiny.
But it's also positioned 760 centimeters away from that 7.6 meters, or roughly 25 feet away.
Okay, so a grain of sand 25 feet from a billiard ball. What about the big planets? Jupiter? Jupiter, the giant of the system on this scale, would be about 40 meters away from the billiard ball sun.
40 meters.
Yeah.
Like half a football field almost.
Getting there. And Pluto, that distant, icy world, now a dwarf planet, of course, would be on this scale 300 meters away from the sun.
300 meters. That's like 3 football fields end to end.
Exactly. So that whole solar system, this vast 10 billion kilometer expanse we talked about, it now fits within the scale of, say, a decent-sized park or maybe a small neighborhood.
That really does help make it tangible. Sun, tiny Earth, 25 feet away. Pluto, 3 blocks down the road. Okay.
But here's the kicker. The immediate humbling realization you get from this model is that even these huge interplanetary distances, 300 meters from the sun to Pluto in our model, they are instantly rendered. Well, Shklovsky called them mere trifles.
Trifles. Compared to what?
Compared to the moment we attempt to look beyond the solar system to the nearest star, our whole neighborhood, huge as it felt scaled down to a park, becomes microscopically small.
Ah, right. So the scale breaks down again immediately.
Completely. We have to ditch kilometers, we have to ditch AU. They just don't work for interstellar measurements.
So what do we use? I know popular science often uses the light year, right?
Yep. The light year is very intuitive. It's simply the distance light travels in 1 year, which is roughly 10 trillion kilometers. That's 10,000 billion, a huge distance, but at least the concept is clear.
Okay, but you said astronomers don't really use that.
Not usually in their technical work, no. The working scientific unit is the parsec, usually abbreviated PC. It stands for parallax second.
Parsec. Okay, how big is that compared to a light year?
1 parsec is equal to 3.26 light years. So it's in the same ballpark, but a bit larger.
Why do scientists prefer it? Is it just tradition? No, it's actually because it's based on a measurable geometric effect called parallax. It's defined quite precisely. A parsec is the distance at which the radius of Earth's orbit, that 1 AU we defined earlier, subtends an angle of exactly 1 arcsecond. 1 arcsecond. That sounds incredibly small. How small is it?
It is minuscule. It's really hard to visualize. Shklovsky gave a great analogy to give you some context. He said it's the angle under which you would see a small coin, like a Russian 1 kopeck coin, just a tiny piece of currency,
Okay.
if you were looking at it from 3 full kilometers away.
3 kilometers. just to see the width of Earth's orbit shrink to that tiny angle.
Exactly. That's how far we have to effectively stand back from our own solar system to make its diameter look like a tiny, tiny angular speck. The parsec is a unit specifically built to handle extreme isolation.
And just how isolated are we? Where's the nearest star in parsecs?
The nearest star system to us is Alpha Centauri, and the closest star within that system is Proxima Centauri. It's about 1.3 parsecs away.
1.3 parsecs, so about 4.2 light years.
Mm-hmm.
Okay. Now, how does that relate back to our billiard ball model?
Here's where it gets really interesting and the model just shatters. Remember, in that model, the sun was a 7-centimeter ball and Pluto was 300 meters away, fitting in a park. If we tried to place Proxima Centauri onto that same scale, it wouldn't be in the same park. It wouldn't be in the same city. It wouldn't even be in the same state or maybe even country, depending on where you are.
Seriously, how far would it be?
On the billiard ball scale, the nearest star, Proxima Centauri, would be 2,000 kilometers away.
2,000 kilometers
Yes.
from our 7-centimeter sun.
Yep. Roughly the distance from, say, London to Rome or New York to Miami. Just empty space.
Wow. Okay. The isolation is just astounding. The density of stuff in our stellar neighborhood is practically zero.
It really is. But since we need a tool to conceptually manage scales far, far beyond even that 2,000-kilometer scales of galaxies and the universe, let me quickly introduce our final and most intensely compressed mental model. We'll come back to apply it later when we map the metagalaxy.
Okay, the ultimate compression tool.
This is the one that really stretches the imagination, maybe snaps it. We're going to take the vast distance of Earth's orbit, 1 AU, 150 million kilometers, and shrink it down to the size of the innermost electron orbit in a simple hydrogen atom.
You mean Bohr's first orbit?
Exactly. The radius of Bohr's first orbit is just 0.53 times 10 to the minus 8 centimeters. That's Better's 0.000000053 centimeters. Absolutely infinitesimal.
Shrinking 150 million kilometers down to that.
That's the plan. This is the ultimate weapon against cosmic paralysis, Shrimpsky implies. A scale so intensely shrunk that we can just maybe momentarily hold the observable universe in our conceptual hands. We'll use this later.
Okay, I'm intrigued and slightly scared. Let's move outwards first. Right. So we've established the overwhelming isolation of our solar system within its stellar neighborhood. Now let's zoom out further, from considering just our single star and its planets to the giant collective of stars and nebulae that houses us. Our home galaxy, the Milky Way. Ah, yes, the galaxy. When you look up on a really dark night, away from city lights, and see that faint, beautiful stripe of light stretching across the sky.
That's the Milky Way.
That's it. You're looking edge-on, directly into the main stellar disk of our galaxy, from the inside.
So structurally, what is it? What's the basic shape?
Well, it's incredibly complex, really. But the first approximation, the sort of classic view, is that it's a highly compressed rotational ellipsoid. Think of a giant double convex lens, or maybe like two dinner plates put together. Or, yeah, a gigantic flat pancake is a common analogy.
A pancake of stars. But you said it's more complex.
Oh, yeah. The sources make it clear that the structure is far from uniform. Different types of celestial objects concentrate in very different ways within that overall structure.
Like what?
Well, the young, hot, massive stars, the really bright blue ones, and also the big clouds of gas and dust, the nebulae where new stars are forming. They're very tightly constrained to the galactic equatorial plane. They really define that thin pancake shape.
Okay, so the young stuff is in the flat part.
Right. But then if you look at the much older stellar structures, like the beautiful ancient globular clusters, those tightly packed balls of hundreds of thousands of old stars.
Yeah, those are amazing in telescopes.
They show almost no concentration towards the plane at all. Instead, they're highly concentrated towards the galaxy center, forming this massive, roughly spherical halo that surrounds the entire disk.
Ah, okay. So it's like a flat disk embedded within a big diffuse ball of older stars.
That's a pretty good way to visualize it. This complex, differentiated structure, with different populations of stars living in different parts, is why just calling it a pancake only gets you so far.
So how big is this disk halo structure?
The main stellar disk, the bright part we see is the Milky Way, has a diameter of about 100,000 light years.
Okay, 100,000 light years across. And how thick is the disk?
The thickness is only about 1,500 light years on average.
Wait, 100,000 wide, but only 1,500 thick. That means it's roughly, what, 60 or 70 times wider than it is thick?
Yep, around 67 times. So that highly flattened appearance is very real. It is like a cosmic pancake in terms of proportions.
And how many stars are packed into this system?
The estimates vary, but a commonly cited number, and the one Shklovsky uses, is well over 150 billion stars. of all sorts of different types, sizes, and ages.
150 billion. And where are we in this vast city of stars? Are we downtown?
Yeah, definitely not. We are way out in the suburbs. Our sun is located near the periphery of the main disk.
Okay, near the edge. Are we in the plane, at least?
Pretty close. We're just slightly above the main equatorial plane, maybe about 30 light years out from it, which is tiny compared to the overall thickness. And crucially, we're about 30,000 light years away from the dense galactic center, the nucleus.
So halfway out from the center to the edge, roughly, living in galactic suburbia.
That's a perfect description. We have a rather unremarkable, quiet address.
And that sense of being in the suburbs is reinforced by the star density, right? It's not evenly spread out.
Not at all. The density of stars near us, near the sun, is actually quite low. It's, well, sparse. But if you could travel towards the galactic nucleus, the density spikes dramatically.
How dramatic are we talking?
We're talking a major, major difference. Down in the galactic core, the stellar density can reach something like 2,000 stars per cubic parsec.
2,000 stars in a box, just over 3 light years on a side. How does that compare to here?
That density is nearly 20,000 times higher than the average density we experience out here near the sun.
20,000 times denser.
And the very, very center of the nucleus, a region maybe only 1 parsec wide, might contain millions of stars crammed incredibly close together. It's a totally different environment.
And this whole enormous structure, disk, halo, core, it's not just sitting there, is it? It's moving.
Constantly. The entire galaxy is a vast rotating system. But it's important to remember it doesn't spin like a solid object, like a frisbee.
What do you mean?
Different parts rotate at different speeds. It's called differential rotation. Sections closer to the center might complete an orbit faster or slower than sections further out. Our section, the part of the disk containing our sun and solar system, is cruising along at a pretty dizzying speed. About 250 kilometers per second. 250 kilometers.
Yeah.
Every single second. That sounds incredibly fast.
It is. But even at that incredible speed, the circumference of our orbit around the galactic center is just so unbelievably vast.
And it takes a really long time to go around once.
Exactly. It takes us about 200 million years to complete just one full rotation around the galactic center.
200 million years for one lap. What do we call that period?
That period is known as the galactic year.
A galactic year, okay.
Now, here's where it gets really interesting, I think, and puts our whole existence into a startling perspective. How old is our solar system, roughly?
The sun and the planets, they've been around for about 5 billion years, give or take.
Okay, 5 billion years old. And one lap around the galaxy takes 200 million years. So if you divide 5 billion by 200 million...
Let's see, 5,000 divided by 200, that's...
25.
Exactly. The sun has only completed about 25 orbits around the galactic center since it first formed from a collapsing cloud of gas and dust.
25 galactic years. That's a shockingly small number, actually. Isn't it? It really implies that the cosmic history of our own star is, in a way, very recent. Shklovsky described it as the sun being in its flourishing age right now. We've only just completed maybe 24 trips around the cosmic block. We're relatively new arrivals on this scale.
Huh. 25 laps. That does change how you think about deep time.
But, okay, even though we're hurtling around at 250 kilometers per second, we need to circle back to that stellar safety paradox we touched on earlier.
You mean, why aren't we constantly crashing into other stars if everything's moving so fast?
Yeah. And the answer comes back to that extreme isolation, that emptiness we established with the parsec and the billiard ball model.
Absolutely. It's all about the density or lack thereof. If you were to sort of treat the stars in the galaxy like they were molecules of a gas, the volume they occupy is almost entirely pure vacuum.
How empty are we talking?
Well, remember, the nearest star is 1.3 parsecs away. The average distance between stars in our neighborhood is something like 10 million times their average diameter.
10 million times. That number is just so astronomical it's hard to grasp. It means our galaxy is fundamentally defined more by empty space than by the stars within it.
Precisely. And Shklovsky puts that 10 million times diameter separation into context.
Yeah.
Think about normal air, like the air in this room right now. The molecules are separated, but only by maybe a few dozen times their own size. They're constantly bumping into each other.
Correct.
To achieve the same level of statistical emptiness, the same degree of rarefaction that exists between stars in our galactic neighborhood, you would have to take normal air and decrease its density by a factor of 10 to the power of 18.
10 with 18 zeros after it. That's a billion times less dense than air.
Something like that, yeah. That's the level of emptiness we're talking about between stars out here.
Yeah.
And that statistical fluke, that near-perfect vacuum, is what guarantees our safety. So the massive implication is, in our region of the galaxy, stellar collisions essentially do not happen. Not over the entire 10 billion year history of the stellar system's evolution. We are statistically far, far safer from collisions than even the air molecules around us. That's pretty much it. The only place where collisions become even remotely possible is right in that incredibly dense galactic center we talked about.
Where the density is 20,000 times higher.
Yeah. Given that density of maybe 2,000 stars per cubic parsec, calculations suggest you might expect, statistically perhaps, one stellar collision every million years or so.
1 per million years. So even in the absolute densest part of the galaxy, collisions are still incredibly rare events.
Very rare, yes.
Mm-hmm.
But they are not non-existent like they are out here in the suburbs. That core is a different beast entirely.
Okay, so safe in the suburbs, dangerous downtown.
Got it. All right, we've established the surprising stellar safety of our quiet suburban neighborhood in the Milky Way. Let's now ask the big question. What lies beyond the suburbs? Beyond our own galaxy? What's out there in the truly massive city that astronomers call the metagalaxy?
Now we're getting into the realm of extragalactic astronomy. And Shklovsky points out that this field really took the leading role in astronomy in the 20th century. It's all about mapping out the observable part of the universe, which is composed of, well, billions of other star systems, other galaxies.
Billions. Okay, let's start close to home again. Who are our nearest galactic neighbors?
Our immediate neighbors are actually pretty substantial galaxies themselves. The closest are the Magellanic Clouds. You can only see them from the southern hemisphere.
Right, the large and small Magellanic Clouds. How far are they? They're about 200,000 light-years away, which sounds far, but crucially, that distance is actually comparable to the size of our own Milky Way galaxy. They are practically right next door, cosmically speaking, and they're considered satellite galaxies of ours.
Okay, satellites. But what about the really big neighbor, the one everyone talks about?
You mean Andromeda. M31, the Andromeda Nebula, or Andromeda Galaxy. It's this gigantic, magnificent spiral star system. On a really dark night, if you know exactly where to look, you can just barely see it with the naked eye as this faint, blurry smudge.
And how far is Andromeda?
It's about 1.8 million light-years away.
Okay, 1.8 million light years. That's roughly, what, 20 times the diameter of our own galaxy away. Still close on a cosmic scale, but definitely further than the Magellanic Clouds.
Exactly. And Andromeda is really a crucial benchmark because it shows the sheer scale of galactic competition, if you like. It's estimated to have maybe 3 times the mass of our own Milky Way.
3 times our mass, so we are the smaller partner in our little local dance.
It seems so, yeah. We're kind of gravitationally bound together, along with some smaller galaxies, in what's called the local group. And Andromeda is the heavyweight champ of the group. Comparing our two systems helps us start to understand the structure of these local galactic arrangements.
Andromeda shows us a big spiral like ours. What other kinds of galaxies are out there?
Oh, there's a huge variety. Astronomers classify them. You have the spectacular spiral galaxies like Andromeda and our Milky Way, those beautiful arms. Then you have spheroidal and ellipsoidal galaxies, which are often older and look more like smooth, featureless blobs of light. They lack the spiral arms entirely.
Okay.
And then you also get irregular structures like the Magellanic Clouds, which don't really have a defined shape, maybe due to gravitational interactions with bigger neighbors like us.
So spirals, ellipticals, irregulars, how many of these things can we actually see out there? What's the galactic census look like?
Well, the numbers get staggering very quickly as you look deeper. Using standard optical telescopes, astronomers can resolve about 250 galaxies that are brighter than what they call the 12th magnitude. That's relatively bright for a galaxy.
Okay, 250 nearby or bright ones.
If you push fainter down to 16th magnitude, that number jumps to about 50,000 galaxies cataloged.
50,000. Getting crowded.
But then, when we use the most powerful instruments, like the big research telescopes, pushing the photographic limits down to something like 24th or 25th magnitude, incredibly faint.
Yeah.
The vast majority of the billions of faint objects captured on those deep sky photographic plates turn out to be galaxies. Billions upon billions of them stretching out as far as we can possibly see. Our observable boundaries just keep expanding rapidly with technology.
Billions. And here's where that time warp idea must come in again, right? When we look at these incredibly distant ones.
Undeniably. The light from many of these extremely distant galaxies was emitted billions upon billions of years ago. We aren't just looking outwards into space. We are literally looking backwards into the universe's deep past.
So we're seeing them as they were billions of years ago.
Exactly. We're seeing light that started its journey towards us long before the Archean period of Earth's geological history, long before complex life evolved here, maybe even before our continents properly formed. It's like looking through a cosmic time machine.
That's incredible. And the scale of energy involved in some of these distant systems.
Yeah.
It also seems to defy easy comprehension, doesn't it? This brings us to the radio galaxies.
Ah, yes, these are fascinating and extreme objects. These are entire galaxies, entire systems that emit absolutely colossal amounts of energy, specifically in the radio part of the electromagnetic spectrum. Sometimes their radio output completely dwarfs their optical light output.
So they're brighter in radio waves than in visible light.
Way brighter, in some cases. The classic example Shklovsky uses here is Cygnus A.
Cygnus A, okay, what's its story?
Optically, if you look at it with a regular telescope, it's incredibly faint. It just appears as two small, fuzzy smudges, about 17th magnitude, barely visible.
Okay, visually unimpressive.
But its intrinsic luminosity, its actual true power output, especially in radio waves, is estimated to be about 10 times the luminosity of our entire Milky Way galaxy combined.
10 times the power of our whole galaxy. From something that looks like a faint smudge. Why does it look so weak then?
Purely because of its immense distance. Cygnus A is 600 million light-years away from us.
600 million light years. Okay, that's a huge distance. How do we grasp the energy involved compared to something local?
This is where the comparison gets mind-blowing. Think about the inverse square law, right?
Yeah.
The intensity of radiation, like light or radio waves, drops off incredibly fast with the square of the distance. Double the distance, the signal is only 1/4 as strong.
Right, signals get weak very quickly over distance.
Yet the radio energy we receive here on Earth from Cygnus A, which has traveled for 600 million years across that vast distance, its measured radio output still exceeds the radio output we receive from our own nearby sun.
Wait. Exceeds the sun's radio output. Our sun is right next door. It's only 8 light minutes away.
Precisely. 8 minutes versus 600 million years. For the signal from Cygnus A, traveling for that colossal amount of time and distance, to overcome the immense weakening effect of the inverse square law and still register as a stronger radio source than our sun.
Means the engine powering Cygnus A must be unbelievably powerful and concentrated.
Beyond easy description, really. It represents a level of cosmic violence, some kind of extreme energetic process happening in its core that is barely comprehensible on human scales. These radio galaxies point to some of the most extreme physics in the universe. And, the detailed study of these incredibly distant and energetic galaxies, looking closely at their light, led directly to perhaps the single most profound discovery in modern science: the expansion of the universe itself. This whole finding hinges on the careful analysis of the spectra of these distant galaxies.
Ah, okay. We're talking about redshift and the Doppler effect, applied to light waves now, not sound waves.
Exactly that. Just like the pitch of an ambulance siren changes as it moves towards or away from you, the color of light from a moving object changes too.
How does that work for light?
Well, if a light source, like a galaxy, is moving towards us, the light waves it emits get kind of compressed, squished together. This shifts the pattern of lines we see in its spectrum towards shorter wavelengths. Towards the blue end of the spectrum, we call that a blue shift.
Okay, towards us, blue shift.
Right. But if the source is moving away from us, the light waves get stretched out. This shifts the spectral lines towards longer wavelengths, towards the red end of the spectrum, and that's called redshift.
Away from us, redshift. So what did astronomers find when they looked at the spectra of all those distant galaxies?
The absolutely universal observation, with the exception of only a very few of the closest galaxies like Andromeda, which are gravitationally bound to us, is that almost all galactic spectra show a pronounced redshift. The further away the galaxy is, the greater the redshift.
So almost everything is moving away from us. And the farther away it is, the faster it's moving away.
That's exactly the conclusion. The universe isn't static, it's expanding, stretching in all directions.
And the speeds involved must be pretty incredible for the really distant ones.
Almost unbelievable. We mentioned Cygnus A earlier, the powerful radio galaxy 600 million light-years away. It's receding from us at about 17,000 kilometers per second.
17,000 kilometers, that's incredibly fast. But you get the sense it's not the fastest out there.
Oh, not by a long shot. The speed records really demonstrate the sheer scale of this cosmic expansion. Back in the early 1960s, a new record was set by another, even more distant radio galaxy called 3C295.
3C295. Okay, what was special about its spectrum?
Astronomers managed to identify a known spectral line in it, a line usually produced by ionized oxygen atoms. Normally, this line appears way out in the ultraviolet part of the spectrum, which is invisible to our eyes and blocked by our atmosphere.
Okay.
But in the spectrum of 3C295, this ultraviolet line was shifted so severely by the redshift that it actually appeared in the visible orange part of the spectrum.
It shifted all the way from UV to orange. That must correspond to an absolutely insane velocity.
It does.
Huh.
When they calculated the recession speed needed to cause such a massive shift, it came out as 138,000 kilometers per second.
138,000 kilometers per second. That's almost half the speed of light itself.
Nearly half the speed of light, yes. An object moving away from us at almost 15% of the ultimate cosmic speed limit.
Wow. And the distance. How far away does that speed imply 3C295 is?
The calculated distance corresponding to that speed and redshift was about 5 billion light years away.
5 billion light years. Hold on. If it's 5 billion light years away, that means the light we're seeing from it today
Left that galaxy 5 billion years ago. Which means that when astronomers observe 3C295, they are looking at light that was emitted at pretty much the exact time when our own sun and planets were just beginning to coalesce and form out of their primordial gas cloud.
So observing 3C295 is like taking an instantaneous photograph of what a part of the young metagalaxy looked like 5 billion years in the past.
Exactly. It's a direct window into the universe's history.
Okay, so if we connect this to the bigger picture, the whole structure is expanding. Galaxies are flying away from each other at incredible speeds. But you also mentioned they're not just spread out evenly, right? They clump together.
That's right. While the overall universe is expanding, gravity is still powerful on more local scales. Galaxies exhibit a very strong tendency to cluster together. This shows that gravity is still winning the local battles against the global expansion.
So what kind of clusters are there? What's our local situation?
Well, as we mentioned, we belong to a relatively small, gravitationally bound assembly called the Local Group. It contains maybe 20 or so galaxies, dominated by us and Andromeda, plus the Magellanic Clouds and other smaller dwarf galaxies.
Okay, the local group is our little galactic game.
Right. But the Local Group itself isn't isolated. It's actually just a minor satellite system orbiting on the outskirts of a much, much larger structure called the Virgo Cluster.
The Virgo cluster, how big is that?
The Virgo Cluster is huge. It contains thousands of member galaxies and really dominates our entire region of the universe. It's the gravitational heart of our local supercluster.
Thousands of galaxies. So the universe has this large-scale structure. It's not uniform. There are these huge clusters. And then what's between them?
Mostly voids. The presence of these massive clusters demonstrates this large-scale filamentary structure like a cosmic web. In the vast empty regions, the voids between these massive clusters, the average density of galaxies is dozens of times lower than inside the clusters. It really is a universe of dense filaments and clusters separated by near emptiness.
Okay, so clustering is key. And Shklovsky makes an interesting point contrasting galaxy clusters with star clusters, doesn't he?
He does, and it highlights a fundamental difference in density and interaction. Remember when we talked about star clusters, or just stars within our galaxy?
Yeah, the average distance between stars is millions of times their own size, incredibly empty. Collisions basically never happen.
Exactly, that 10 to the 18 times rarefaction compared to air. But now think about a galaxy cluster like Virgo. What's the situation there?
Are galaxies also super far apart compared to their size?
No, completely the opposite. Within a dense galaxy cluster, the average distances between the galaxies are often only a few times larger than the diameters of the galaxies themselves. They're packed relatively close together.
Only a few diameters apart, so they're practically rubbing shoulders, cosmically speaking.
Pretty much. They are constantly interacting gravitationally, pulling on each other, sometimes merging, sometimes stripping gas from each other. It's a much more dynamic and crowded environment than the space between stars.
Which leads to Shklovsky's fascinating metaphor about viscosity.
Yeah, it's a great one. He says, if you were to sort of treat the entire metagalaxy as a giant, incredibly massive gas, where the individual galaxies are the molecules,
Okay.
then that medium, that galaxy gas, would be extremely viscous. The galaxies are moving through space, yes, due to the expansion, but they are constantly subject to immense gravitational drag and strong tugs from their near neighbors within the clusters. It's not a free-for-all.
Wow, what a contrast. Our solar system within the galaxy is defined by statistical emptiness and near-zero interaction between stars. But the metagalaxy on the largest scales is defined by the statistical viscosity and constant interaction between galaxies and clusters.
It's a stunning dichotomy of scales, isn't it?
It's yes, locally.
Stickiness globally.
So to truly try and contain this mind-boggling picture, from the tight packing of galaxies and clusters to the near light speed expansion to the billions of years of look-back time, we absolutely have to return to our final, most hyper-compressed mental model.
Ah, the Bohr atom scale. Ready to shrink the universe down to the size of a lab bench.
Let's try it. Let's see if we can actually hold the observable universe within a framework the size of maybe a few city blocks. Just remind us of the core scaling factor.
Okay. In this model, we take the entire orbit of the Earth around the Sun, that 1 AU, 150 million kilometers, and we shrink it down to the radius of the first electron orbit in a simple hydrogen atom. That's Bohr's first orbit, a radius of just 53 times 10 centimeters. Absolutely tiny.
Okay, Earth's orbit equals less than a billionth of a centimeter. On that scale, where's the center of our own Milky Way galaxy, which is 30,000 light years away in reality?
On this intensely shrunk scale, the center of our entire galaxy is only 10 centimeters away from us.
10 centimeters? That's like the width of my hand.
Pretty much. And the entire 100,000 light-year diameter of the Milky Way disk would span only about 35 centimeters across in total. Fits on a dinner plate.
Unbelievable. Okay, what about Andromeda? Our big neighbor, 1.8 million light years away in reality.
On the Bohr orbit scale, Andromeda M31 is just over 6 meters distant from us, like across the room.
6 meters. Okay, now for the big ones. Cygnus A, that powerful radio giant we talked about, 600 million light years away.
Cygnus A on this scale is 2.5 kilometers distant, so maybe a brisk walk away.
2.5 kilometers. And finally, the record breaker. 3C295, the galaxy receding at nearly half the speed of light, 5 billion light years away in reality. Where is it on this Bohr scale?
3C295, representing the edge of what we could see back then, 5 billion light years distant, is situated 25 kilometers away from us in this scale model.
25 kilometers, roughly the size of a large city.
Exactly. That model, where 25 kilometers represents 5 billion years of light travel time and distance, is perhaps the only way, as Shklovsky suggested, to genuinely fit the vastness of the metagalaxy into a conceptual space that the human mind can navigate without completely paralyzing itself with those monstrous numbers.
Hold the universe in the size of a city. It's extreme, but maybe necessary. Okay, we've built these incredible scale models, shrunk things down, but it is absolutely critical to remember, as Shklovsky emphasizes, that this entire vast structure we've been describing is not static. It's not like looking at a fixed photograph.
Yet at all. Everything is dynamic. Everything changes, everything evolves. Stars are born and die, nebulae coalesce and dissipate, galaxies collide and merge, and the very structure of the metagalaxy itself, the expansion rate, the clustering, it all changes over cosmic time.
And we have actual evidence for this change over time, right? It's not just theoretical.
Oh, absolutely. The dynamic nature of the universe was profoundly confirmed back in 1965 with the accidental discovery of the relic radiation, what we now call the cosmic microwave background, the CMB.
The afterglow of the Big Bang.
Essentially, yes.
Yeah.
This faint residual heat, pervading all of space, provided direct, undeniable evidence that the universe in its earliest stages, billions of years ago, was qualitatively different from the universe we see today. Hotter, denser, more uniform.
Wait, how different are we talking about? Qualitatively different means what?
We're talking about a time before any of the structures we've discussed existed. In those initial, incredibly dense, hot moments after the Big Bang, there were simply no stars yet. No galaxies, no heavy chemical elements like carbon or oxygen, which are necessary for life as we know it.
No planets, no life.
Definitely no life. The conditions were far too extreme. The CMB radiation confirms that we observe a grand, ongoing process of cosmic evolution, a universe that has been consistently moving, as Shklovsky puts it, from the simple to the complex over billions of years.
Okay, so we have this immense sweep of time, maybe 15 billion years of cosmic history, required for this evolution from a simple hot state to the complex universe with stars, galaxies, planets, and us. How can we possibly grasp that timescale?
Well, just like we needed scale models for distance, we need one for time. And the most famous one, popularized by Carl Sagan but building on earlier ideas, is the cosmic calendar.
Ah, yes, the cosmic calendar. Explain how that works again.
It's brilliantly simple. You take the entire estimated history of the universe, let's say roughly 15 billion years, and you compress it all down into a single metaphorical calendar year. January 1st at midnight is the Big Bang, and December 31st at midnight is the present moment.
Okay, 15 billion years fits into 1 year. What does that make the scale factor? Like how much real time is a day or a second on this calendar? The scale of this compression is, again, truly humbling. In the cosmic calendar, the scale of this compression is, again, truly humbling. In the cosmic calendar, one cosmic month is about 1.25 billion real years. The scale of this compression is, again, truly humbling. In the cosmic calendar, one cosmic day is about 40 million real years. The scale of this compression is, again, truly humbling. In the cosmic calendar, one cosmic hour is about 1.7 million real years. The scale of this compression is, again, truly humbling. In the cosmic calendar, one cosmic minute is about 28,000 real years. The scale of this compression is, again, truly humbling in the cosmic calendar. And one single cosmic second represents about 500 real, actual years of history. Wow. 500 years flashing by every second on this calendar. The entire history of modern science happens in the last couple of seconds of New Year's Eve.
Exactly. It shows just how much has happened, cosmically speaking, and how recently we arrived on the scene.
The calendar also dramatically highlights this contrast in evolutionary speeds you mentioned, doesn't it? Between the universe itself and life on Earth.
It really does. When you map out major cosmic events on this calendar, universal evolution, the formation of the first matter, the first stars, the formation of galaxies like the Milky Way, which happens around May, it seems to proceed relatively quickly in the beginning, consuming the first few cosmic months.
Okay, the universe gets its basic structure down pretty early in the cosmic year.
Right. But then, when you look specifically at the history of life on Earth, the formation of Earth itself happens around early September on this calendar.
September, so 2/3 of the way through the year already.
Yep. And the first simple life maybe appears soon after, but complex life, dinosaurs, mammals, all of that, it's crammed into the last month or two, mostly December.
So, the rapid cosmic changes seem to settle down relatively early in the year, and then begins the incredibly slow, drawn-out, painstaking process of biological development here on our planet, requiring the last third of the entire cosmic year just to get to us.
It appears that way, yes. A kind of reverse pattern. Fast cosmic evolution early on, followed by very slow biological evolution later, at least in our specific case. Which leads directly to Shklovsky's point about the anthropocentric view that's kind of inherent in how we construct this calendar.
Exactly. If you connect this back to the bigger picture, the sheer focus on Earth's biological development in the standard cosmic calendar is really striking when you think about it.
What do you mean?
Well, look at how detailed the end of the calendar usually is. Everything that happens after, say, September, the formation of Earth, and especially the month of December, it's almost entirely focused on the specific, local developmental stages of geology and life on this one planet, Earth.
Like Cambrian explosion, dinosaurs appear, dinosaurs vanish, mammals rise, humans evolve, all crammed into late December. Right, it becomes a timeline heavily weighted towards our own history. It's sort of a self-serving timeline, you could argue.
So the structure of the calendar, especially the end part, is really defined by the speed or maybe the slowness of biological evolution happening right here, it seems to be. And Shklovsky's implied point is fascinating. Imagine a cosmic calendar constructed by the intelligent inhabitants of a planet orbiting a much older star, perhaps in a galaxy that formed way back in, say, March or April of our cosmic year, a star born billions of years before our sun.
Their cosmic calendar would look completely different, wouldn't it? Their December would be filled with their planet's milestones, reflecting their own local history, which might have started billions of years before ours.
So our sense of what's important in cosmic time, what deserves the detailed attention at the end of the year, it's entirely skewed by the particular, maybe slow-moving process of life evolving here.
That seems to be the implication. This apparent mismatch, the rapid early cosmic change, followed by this seemingly slow biological crawl on Earth, is perhaps one of the deepest temporal mysteries we grapple with when we think about our place in the universe and the possibility of life elsewhere.
Okay, so let's try and wrap this up. What does this all mean for us, trying to navigate these scales? We started by acknowledging that monstrous, potentially paralyzing psychological scale of the universe.
And we armed ourselves, following Shklovsky, with some essential mental tools. We used the astronomical unit, AU, for our local solar system measure, the geometrically precise parsec for interstellar navigation, and that incredibly intense Bohr atom scale to try and visualize an entire cosmos.
We made the solar system tangible with the billiard ball analogy, which starkly revealed the isolation placing our nearest stellar neighbor, Proxima Centauri, an unbelievable 2,000 kilometers away on that human scale.
Then we zoomed out to our home galaxy, the Milky Way. We found our sun's true age is a mere 25 galactic years, only 25 laps around the block. And we reinforce just how safe we are from stellar collisions out here in the burbs, thanks to that almost unimaginable emptiness between stars.
Then we pushed out further into the metagalaxy. We saw we could observe light from incredibly distant systems like the radio galaxy 3C295, light that left 5 billion years ago when the galaxy was receding at nearly half the speed of light. A direct look into the past.
And we wrestled with that profound scale contrast presented by Cygnus A, a galaxy 600 million light-years away, whose radio energy output still dominates our nearby sun, only 8 light-minutes away, completely defying the inverse square law through sheer concentrated power. It hints at extreme processes.
And finally, we condensed all 15 billion years of cosmic history into that single cosmic year. And the big realization there was just how late everything significant to us happens. The entire history of complex life on Earth is restricted to just the final few weeks of that metaphorical calendar, really revealing our own temporal bias.
Yeah, the anthropocentric nature of how we view time becomes really clear.
So the really profound realization seems to be this intimate marriage of cosmic distance and cosmic time. The light we see from the farthest galaxies isn't just from far away, it's from long, long ago. Specifically, it left those sources at a time before our sun and Earth even existed.
Exactly. And that leads to the final provocative thought Shklovsky leaves us with, connecting scale, time, and life.
Which is?
Well, given that massive, unavoidable billion-year time delay between light being emitted from distant galaxies and us finally receiving it,
Yeah.
and given how slowly biological evolution seems to proceed, at least based on our one example, compared to how quickly the universe set its stage early on, what does this suggest about the possibility of highly advanced, intelligent life existing right now in those galaxies that are billions of light years away?
Yeah.
We are currently seeing the light from a time when they were maybe still in their primordial stages, just like our solar system was when 3C295's light left. If complex life took billions of years to evolve there too, any signal of their current advanced state, any knowledge they might possess now,
Is still out there, speeding towards us through the void, but it will always arrive billions of years too late for a conversation. We're perpetually looking at their past, and presumably they'd be looking at ours.
that seems to be the profound implication of these monstrous scales of space and time. The knowledge might be out there, but the universe's very structure imposes this ultimate, insurmountable delay. A rather humbling thought to end on.